Welcome to the third lecture on module theory. In the first two lectures, we have discussed modules, submodules, and module homomorphisms. Today, we will discuss quotient modules and isomorphism theorems. So, we will start with the definition of quotient modules. Let M be an R module and N be a submodule of M. Then, we define quotient module of M mod N in this way. So, M with respect to addition, this is an abelian group. Now, if you consider a submodule of M, then that is in particular an additive subgroup. Since M is abelian, so this additive subgroup, it is normal subgroup. So, we can consider this quotient group M mod N, where elements of M mod N, it looks like this kind of coset. It is just x plus y, where y varies in n. And collection of all cosets, if you vary this x in M, then they form a partition, and you can define addition on this coset. For example, x plus n. Let us say x1 plus n plus x2 plus n, you can define as x1 plus x2, its equivalence class. So, in this way, M mod n, this is an additive abelian group. Now, the question is, can you make it into an R module? So, we have to define the scalar multiplication on M mod n. But we already have scalar multiplication in M, so using that we can define scalar multiplication in M mod n as follows. So, you pick a scalar, that is element from R, and you pick a coset x plus n, that is an element of M mod n, then you can multiply them in this way. So, it is just equivalence class of R times x. Why well definedness? Because we are working with this coset, and this coset, it may have other representatives. So, this definition, it is independent of the choice of the representatives of this coset that we need to prove. For example, let us say x plus n, it is same as y plus n, then that means their difference x minus y, it is there in n. Now, if you multiply this difference by r, then r times x minus y, it is belongs to n, because n is a submodule of M and n is closed under the scalar multiplication. Now, this thing, it proves that r times x minus r times y belongs to n. So, r times x, its equivalence class, it is same as r times y, this equivalence class. So, this scalar multiplication, it is well defined, and now you can verify that this satisfies all those 5 properties in the definition of the module. Thus, M mod n, it is an R module, and that module we call it quotient module. So, it is quotient module of M by the submodule n. Once we have this quotient module M mod n, then there is a natural map from this R module M to the R module M. It is defined as follows. So, you consider an element of M, then you can map to its equivalence class, that is the coset represented by this element x. And is it an R module homomorphism, one may ask. So, one can verify that this is not only an R module homomorphism, but also it is surjective R module homomorphism, such that kernel of this map, it is just n. So, let me quickly prove this proposition. So, we want to prove that this is R module homomorphism. That means we need to verify that it preserves addition. What is phi of x plus y? It is just equivalence class of this one. but by definition of quotient module, it is just x plus n plus y plus n, and this is pi of x plus pi of y. And similarly, one can prove that it preserves scalar multiplication as well. So it is r times pi of x. And why it is surjective? Because each element of M mod n, it looks like this for some x coming from M. So this is surjective R module homomorphism. And what about its kernel? So as we can see, its kernel is n. How to prove that? So suppose pi of x is 0. That means it is if and only this coset, it is just the 0 element of M mod n. And what is the 0 element of M mod n? This is just this trivial coset. And it is equivalent to say that x belongs to that submodule n. Moreover, this quotient module, it satisfies this universal property. So suppose M is an R module and n is a submodule of M, then for every homomorphism from M to L, there is a unique homomorphism phi bar from this quotient module M mod n to L, such that you have this thing if and only if something happens. So if and only if n is a submodule of kernel of phi. So if we write this diagram, then it says that suppose you have a module homomorphism from M to L, and you already have this natural projection map from M to M mod n. Let's say it is pi and this is phi. Then this is, one may ask that when can you lift your module homomorphism phi to a module homomorphism from M mod n to L? So that is the question. So you can lift phi to a module homomorphism from M mod n to L. So there exists unique phi bar such that this diagram is commutative if and only if n is a submodule of kernel phi, or n is contained in kernel phi. So let's prove this proposition. One part is trivial. Let's say suppose phi is a module homomorphism, and for every homomorphism you can lift it to a module homomorphism from M mod n to L. And now you want to prove that n is contained in the kernel of that module homomorphism. So here you consider an element of n, and suppose this module homomorphism you can lift to phi bar such that you have this equality. So phi equal to phi bar compose pi, and now you want to prove that this x, it is there in kernel phi. Okay, so you just take phi of x, it is same as phi bar compose pi of x. And what is pi of x? It is just x plus n. But since x belongs to n, this x plus n, this is just 0 element in the quotient module. So it is phi bar of, it is, you may write 0 or 0 plus n. And what is the image of the 0 element? Under any module homomorphism, it is a 0 element. So this is 0 element of L. Yeah. So x is there in kernel phi. Now what about reverse direction? So suppose n is a submodule of M, and let phi from M to L an linear map such that you have this condition. Then we want to prove that this kind of linear map, we can extend it to a map from M mod n to L such that this diagram is commutative. That is the meaning of lifting. So you can lift your map phi to a map from M mod n to L. So we should define, so we should prove both existence and uniqueness of phi bar. Okay, so we define phi bar in this way: M mod n to L by phi bar of any element of M mod n. It looks like this, x plus n, it is left coset, and we define this as phi of x. So using phi, we are defining phi bar. Now we need to check whether this map is well defined or not. For example, if x plus n it is same as y plus n, then it is if and only if x minus y belongs to n, and if you apply phi on that, then that gives that phi of x, phi of x minus y, that is 0, because n is contained in kernel phi and x minus y is there, so x minus y is there in kernel phi. So phi of x, it is same as phi of y. So this proves that phi bar, this definition, if we define phi bar in this way, this is well defined map. Now only thing we need to verify that it is an R module homomorphism. Moreover, we need to verify that this diagram is commutative, that means this equality, and then we will prove uniqueness. So for uniqueness, we will just prove, so suppose you have two maps phi1 and phi2 from M mod n to L such that you have this condition. So you have phi, it is same as phi1 compose pi, that is same as phi2 compose pi. Now you need to verify that phi1 is same as phi2. I will leave this thing as exercise, but main idea, so existence, it follows from this, and only thing you need to check that this is R module homomorphism, and this kind of map, it is unique. And now we will discuss the first isomorphism theorem. So you start with an R module homomorphism, let's say phi from M to N, then we have this isomorphism. So using the universal property of quotient module, we can define a map from this quotient module to phi of M, or directly we can give an isomorphism. So here is the proof. So we directly define a map from this quotient module to phi of M. So I should note that phi of M, this is a submodule of N, and kernel phi, this is a submodule of M, and if you go modulo that submodule, then this is the quotient module. So both are R modules, and we are defining a map from this R module to phi of M as follows. So you define phi of x bar, so any element of this quotient module, it looks like this, so it is equivalence class of x, so we just denote in this way. So phi of x bar, you just define it as phi of x, and again you need to verify that this is a well defined map, set map, and then you need to check, so we should verify the following properties. So phi is well defined, and for that, so let's verify this one by one. So suppose x bar is same as y bar, that means equivalence class of x, it is same as equivalence class of y, and the meaning of that the difference between the representatives of these two equivalence classes, that should be there in kernel phi, and then that implies that phi of x, it is same as phi of y. Okay, so this is well defined map, and now you can verify that it preserves addition. So x1 bar plus x2 bar, it is same as phi of x1 plus x2 whole bar, and by definition this is just phi of x1 plus x2. Since phi is an R module homomorphism, this is same as phi of x1 plus phi of x2, and this is same as capital Phi of x1 plus capital Phi of x2. And in same way you can define that it preserves scalar multiplication also. So this is an R-linear map. And why this phi is injective? It's easy to verify, because if phi of x bar it is 0, then that implies that phi of x is 0. That means x is there in kernel phi, and that means x bar, that equivalence class, that is 0, because we are going modulo kernel phi in that quotient module. And why this is surjective? Because we are considering this module phi of m. So your codomain is phi of m, and here any element, so this is the collection of all the images of phi. So any element of phi of m, it looks like phi of x for some x coming from m. So this is surjective, and thus this phi, it is actually a bijective set map, and it is R-linear map, that is module homomorphism. So this is a module isomorphism. Yeah, we have this isomorphism. So these two modules, these are isomorphic. Next we will define sum of submodules. So you consider A and B, both are submodules of M. Then how can you define their sum? So we can define the sum of A and B in the obvious way. So this is just notation, A plus B we write, and what is this? By definition it is just A plus B, where that element A is coming from the submodule A and element B, it is coming from the submodule B. Now one can verify that this is a non-empty subset of M. Why? Because 0 element is there. So 0 plus 0. So 0 is there in A as well as in B, 0 element of M, I mean. So A plus B, it contains the 0 element of M, so it is non-empty subset. Now if we prove that A plus B, it is closed under addition as well as scalar multiplication, then this A plus B, it is actually submodule, and these things are very easy to verify. So A plus B, this is a submodule of M, and we call it sum of the submodules A and B. This concept, it can be generalized to arbitrary family of submodules. That family of submodules, it can be finite, infinite, countable, uncountable, whatever. But you consider an arbitrary family of submodules, let's say A alpha, and alpha is indexed by this gamma, and this index set, it can be finite or infinite. Then the sum of those submodules, it is defined to be, so we denote in this way, it is sum of A alpha, where alpha is varying in gamma, and this is just collection of all x alpha, where x alpha is coming from A alpha, and the only restriction we have that all but finitely many components are 0. So except finitely many alpha, all x alpha are 0. And again you can verify that this is a non-empty subset of M, and this is closed under addition as well as scalar multiplication, and we call it sum of these submodules, this family. And next we state our second and third isomorphism theorems. So second isomorphism theorems, it's about the sum of submodules. Note that A intersection B, this is a submodule of A, we just denote in this way, less than or equal to, and B, that is also a submodule of this sum A plus B. Now this first statement, it says that you take the quotient module of A plus B by this submodule, it is same as quotient module of A by this submodule. And how to prove that? So again we want to use first isomorphism theorem, and for that first of all we need to define a module homomorphism. In fact here we can define surjective R module homomorphism, and the natural direction it would be to define a map from A to A plus B modulo B, because A is a submodule of A plus B, so you have that inclusion map. And now from A plus B to A plus B modulo B, you have a natural projection map. So by taking their composition, you can define an R module homomorphism from A to this quotient module. Or directly we can give the map like this. So you start with an element of A and you just map it to the equivalence class of A modulo B. And then we need to verify that this phi, it is actually an R linear map. So you can verify it directly, and as I said that this is composition of two maps, one is inclusion map, another one is projection map. So this is R linear map. Why it is surjective? Because any element of this quotient module, it looks like, I should write that it looks like A plus B modulo B, and this is same as the equivalence class of A only, because this B, it is an element of B. So, or in other words, the difference between this and this, it is B, and that is an element of this submodule B. So this phi, it is surjective. Why the kernel of phi is this intersection? Because, so suppose phi of A, it is 0, then it is equivalent to say that A plus B, it is 0 element of this quotient module. So this is just B, and it is equivalent to say that A belongs to B, and A is already there in the submodule A, so it is equivalent to say that A is there in the submodule A intersection B. So kernel phi, it is just A intersection B, and this is a surjective R module homomorphism whose kernel is this one. So by first isomorphism theorem, we can have this isomorphism from A mod A intersection B to A plus B modulo B. The second statement, we call it third isomorphism theorem, and this is, so you consider two submodules A and B of M, and suppose you have a relation between them. So A is contained in B, then it is saying that first you go modulo A and then you go whole modulo B mod A, that is same thing as going modulo B of M. So if we prove this, so natural way to define a map would be, so you try to define a map from M mod A to M mod B, because any element of M mod A, it looks like this equivalence class. You just send it to the equivalence class of X, but here modulo B. And again one can verify that this is well defined. Why? So we should prove that this is well defined map because we are working with this equivalence class, and an equivalence class, it may have many representatives. So let's say X plus A, it is same as Y plus A, okay, then it gives that X minus Y, it is there in A, but A is contained in B. So X plus B, it is same as Y plus B. So this map is well defined, and this is a linear map. So it's very easy to see that it preserves addition and scalar multiplication. So this is a linear map, and also it is surjective because any element of M mod B, it looks like this, an equivalence class of X where X is coming from M. So this is surjective or linear map. And what is the kernel of this map? So kernel of psi, I claim that this is just B mod A. How to see that? So if psi of X plus A, it is 0, that means X plus B, it is 0. It is if and only if condition, and this gives that X is there in B. Okay, so that means if and only, so x plus A, it is there in B mod A. So kernel is this one, B mod A. And then you can use first isomorphism theorem to have this isomorphism. And next we will discuss our fourth isomorphism theorem, and we call that isomorphism theorem as lattice isomorphism theorem. So first we should recall the definition of lattice. What is lattice? So it is a set with a partial order. We call it partially ordered set, where every two elements have a unique supremum. And what is the meaning of that? It is just list every two elements that should have least upper bound or join, and a unique infimum, that is greatest lower bound or mid. For example, so you consider an R module M, and suppose Lm, this is just collection of all the submodules of M. I claim that this is a lattice with the partial order defined by this. So N1 and N2, suppose these are submodules of M, then N1 is less than or equal to N2, you define this partial order if N1 is contained in N2. So by containment relation we can define a partial order, and we can verify that this gives a partial order, because containment relation, it gives a partial order. And what is partial order? It is just a relation on a set such that that relation is reflexive, antisymmetric and transitive. So one can verify that this gives a partial order. And we want to prove that this collection, with respect to this partial order, it gives a lattice. Why? Because you consider two submodules M1 and M2 of M, then we want to prove that this M1 and M2, they have unique supremum or least upper bound. And what is that? So you can consider M1 plus M2, this sum, and by definition M1 is contained in this M1 plus M2, and M2 is contained in this, and this is the least upper bound, because this is the minimal submodule of M which contains both M1 and M2. So this is a least upper bound, and this is unique. And it also, so M1 and M2, they also have infimum, that is greatest lower bound, namely their intersection M1 intersection M2. So this will be the infimum of M1 and M2. Yeah. So thus this collection of submodules of M, they form a lattice with respect to the partial order defined by this. Now this fourth isomorphism theorem, and what is that? So it says that you start with an R module M, and suppose N is a submodule of M. So it gives a relation between the submodules of M mod N, that quotient module, and the submodules of M that contain N, and that is 1-to-1 correspondence. So it is a bijective correspondence, and this correspondence will be given by this. So you start with a submodule of M that contain N, then you can consider this quotient module P mod N, and you can verify that this is actually a submodule of M mod N. And the map in the other direction, it will be this one. So you start with a submodule of M mod N, and now we want to define a submodule of M that contain N in the most natural way. So if you consider this natural projection map from M to M mod N, so we are considering a submodule of M mod N. And now we can consider the pre-image of this submodule. So then this will be a submodule of M. So this is same as the pre-image via this natural projection map. So it is pi inverse of K. an inverse image of any submodule that will be a submodule of the domain. So this pi inverse k, this is a submodule of M, and one can also verify that this submodule it contains n. Why? So you start with a submodule of M mod n, then that gives a submodule of M, and one can argue that it contains, because in other words you pick anything from n, then pi of x it is just 0, and this is always there in k. Okay, so inverse image of k it contains n in that way. Okay, and now one can verify that these two map they are inverse of each other. So if you denote this thing as phi and this as psi, then verify that this is identity and psi compose phi, this is identity. Why does it call the lattice isomorphism theorem? Because we have just given a one-to-one correspondence between this lattice and this lattice. So this is the lattice of submodules of M mod n, and this one it is the sublattice of the lattice of submodules of M. Now here we should argue that this correspondence it is not only a bijective correspondence, but it gives a lattice isomorphism. And what I mean by that, so this correspondence phi and psi they respect the partial order. So you consider two submodules of M such that they contain n, and then corresponding submodule of M mod n you can have, that is P1 mod n and P2 mod n. Now if you have a relation between P1 and P2, then that gives that is if and only if there is a relation between this P1 mod n that is contained in P2 mod n. Moreover, you consider these two submodules and suppose their supremum, that is this one P1 plus P2, and their infimum, that will be the intersection of P1 P2. So then this diagram there is a one-to-one correspondence between the diagrams of these two lattices. So here corresponding element you will have that this modulo n, and here you will have P1 modulo n, here you will have P2 modulo n, and there is a relation, and their infimum will be P1 intersection P2 modulo n. So this is just P1 modulo n whole intersection P2 modulo n, 1 modulo n plus P2 modulo n. So it preserves the maximum element and minimal element. So there is a lattice isomorphism. That is why we call it lattice isomorphism theorem. I'll stop.